We should close the door or okay. I think the first few minutes you can cut off, so it's is that okay? I know it's not a big workshop, so um I like to do in most of the time of the workshop I don't like to do a big group of people, but mostly in a small group. And I think it's a good setup for me. And we can have more interactive in the workshop and in this 1.5 hour. I know it's the last section of the day, like before the dinner. Yeah, let's get started. So my name is Yu-Feng from OpenGeoHub, and I'm wanting to introduce a little bit of global ensemble digital terrain model and what is the section work. How can we access and improve it with the airborne lidar? So before I get started, I maybe have some idea about what's your intention to get from this workshop and how much you know about digital terrain model. So who else is already work with digital terrain model right here? Can you raise the hand? Oh, okay.
Yeah, I do GIS.
Uh, Yeah, so I think, yeah, it's most of the time we use that as the base mat for like local region, and then we applied some feature. Also, it can be served as the base mat. Hell shape mat is being used very common. So we don't have to actually go to global because this project that we're going also more localized. It's not about like global mapping, this fancy stuff like everyone in the projects are currently doing to map everything in global high resolution. Or it's more like how can we build up a community? How can we have a system that people can easily contribute it? And this is the ideas behind this work. So I would describe this as some of my project. We will start big to have a global view, and somehow this is not really down to earth. And getting more user feedback and participation of the data to use the data to improve part of them. It's the most. It's kind of like maintenance work, but this helps a lot to actually improve things and also um, yeah, how for the community and actually benefits for the end user. So I want to start a little bit from we had in the last presentation I gave in yesterday about the federal framework that I proposed. So I did something test of this kind of framework, and also we are currently in the process of writing a publication together with other researcher in the geomorphometry. And this is like a draft concept, and then we're testing it out and keep improving and adding more features in there. So what is the original concept here is we wanted to create a product called GEDTM Plus. They can combine all the free and open source global digital terrain models and local dams. And this product will serve as a continuous update framework for open source community and software and data. And what's that mean? The continuous update. It means that it should be easier or least overhead to update it by individual. So most of the time that we found the problem of global data set is the money should be plugged into the research group in order to update, because there are so many things they have to fix before they update the new map. For example, you have the new data in, and you probably have to retrain the model, and the model will be slightly different than the version one model, and then you have to spend maybe 3 months to 6 months actually figuring out how to update it. Although that the first time maybe it's still even harder, but it's not easy to update these unless you have funding to plug into the product. So most of the project, if the data are not being used that often, they just stop as the funding run up. But this project I would like to design is really can be updated even like an individual like me. I have ability for maybe 2 hours or 3 hours or even like a week. I can update it and publish a new version, and someone else can also contribute to do that. So it should be relatively simple. So it's a simple method I will introduce, and So this part, the ensemble part, will be simple methods that should be simple, that can be realistically updated in the very low overhead. So that's all that's about. And the third, it should be also have potential to commercialize and privatize of this product. And this is also part of the design to attract more people to actually contribute, because we have to say that this is free license. You can always order the license as much as you like. So you can do the commercial license as you produce, or you can use a CC BY license to increase your citation if you are a researcher. So that's all that the framework is about. And so when we start with this global GEDTM, I think that you guys have heard the presentation, so I will do some stuff like to see actually where is it and how to access it. So I think it's the easiest way, you can just go to Google. If you have a laptop, you can play with that. So if you go Google search, and yeah, we are actually under this one, Open Land Map, GEDTM30. So if you are interested in playing one around this, you have time to spend. If you are coming like to spend kill time, listen to me. You can also just watch. But if you are also wanting to play a little bit, you can try to access here. And just let me know if you have any question, any issue like to accessing, you cannot find it. Just let me know. I will try to help you to find it. So I give you some time. You can find this project on the GitHub. Yeah. Is it easy to find? Okay. Oh, I'm so happy because it shows that in the Google search it has been.
I already did that before you showed it, so not that many other projects called GEDTM30.
Jet. Probably I don't like that name too much. Jet. This is from the ensemble. So it's a ensemble. This is a product name. So this is how Tom like to say that we need to have a product name that's easier.
I mean, you should have the key from global as cancel. So then you have the key.
Okay, thank you. Yeah. So here's a typo. Fix the type. Thank you. Hey, you have to tell me earlier. Anyway, I will fix this later. Come on. And when you play around, actually, we have a lot of issues. So I have been posting it around. You can see that what is the issue they have been raised around. And this is okay. This data is actually not good, and there's some vector pixel problems. There's the issue that I posed in my preprint process. So when I was trying to publish this paper, they already pushed this GitHub online, and people start commenting. And also, I have one release over here in June. So during the conference of geomorphometry in Perugia, I also released this version 1.1 update because we spot some issue as our modeling process, and then we try to fix this water issue with the JRC water mask to fix the water pixel value, which is not realistically rough, as I was originally doesn't care about that because I don't work with water pixel. But the people, I think somebody said, yeah, this water pixel is really not good, and they want me to fix it. So I was trying to find more conservative way to fix the water pixel. So that is based on the feedback that we have this. And also there was a serious issue with the tile boundary arrow because we're trying to map the global ensemble DTM by tile. And then we found out there's one issue in the random forest that they don't extrapolate well for the range. So we use kind of like a schema for the global model to replace the local model, as the local model have higher uncertainty than the global one. So it's more like uncertainty based to choose the best model if the local model have very screw very noisy or imbalanced samples that we shouldn't use, because at some places, for example, some islands only have few 2 3 samples. But if this is a global part project, so we map things in parallel, so we cannot check every tiles. But in this way, we are able to locate most of the problem people provide to us, and then to fix those problems. So this is some of the thing that we go through a lot, and we have the new version update and stuff. And everything is keeping track in the issue cases and also the front page. So there's having some important notes update about what has been changed throughout the time. And I want to show you that this is the current data. It's just in the URL link. So if you use Control Plus, and you can already download it. And please don't download it because it's 400 gigabytes right now for the single file. So this is not the ideal way that I will recommend people to do, because it's just. But if you only want to have it in your infrastructure, yes, if you have the HPC or storage to put all the data there in one place, you can do it. Maybe one day you will finish the download and you're already at your place. But if you are like a small user, usually we just recommend people to directly access to the S3 link. And all of the data that we use, we actually making to cloud optimized GeoTIFF. Is everyone familiar with this cloud optimized GeoTIFF? Yeah, I think in this project it should be spent a lot by our people. Yes.
So what mentioned, I guess, allows you to just query a small part file.
Yep. Yep. And also one other good feature of the cloud optimized GeoTIFF, it's also I would like to show. It's this feature. So you can just put a link over here. Then they start loading the data. And I can load the whole map into QGIS. Yes.
There was a C optional.
Yeah. So because I have a HTTP link, so my link is my proto is from HTTP. I don't have a S3 protocol for our server. So our server exposes things as HTTP or HTTPS. And this is HTTPS, which is like a SSH key. So it's more like a private, more like secure assets from the internet. And this is how like OpenGeoHub we expose the data set. And this is the good features that you can just open it up in the QGIS to have the overview. And yeah, my QGIS is also not really happy for most of the time. I need to change the laptop. Basically, my boss say my laptop is already gone. So wait, let me reopen the Windows again. Yeah, because it's not really.
So when you're opening it with this cloud automated way, it just a subsample that's small. How does that?
Yeah. So when we go GDAL info. So they shows that okay, this link, my GDAL is not really good with my laptop. Wait, wait, this is strange. Let me see. I missed one. Yep. So when you open in GDAL, you can see that here's we call it overview. So the overview is work as extra layers for GeoTIFF. So the overview, it's like if you have like a whole 30-meter pixels, whole 30-meter pixels resolution, you will have the pixel size as this big. So it's like 12 million multiplied by 540,000. And when you do the overview, you actually aggregate those pixels into bigger pixel size, so lower resolution. And each overview work as a pyramid. So the biggest layer on the bottom have all of the pixel, But when you zoom out, you don't need all of the pixels to be visualized because the human eyes cannot also distinguish that. So they get the overview to aggregate all this pixel to smaller pixel numbers. And until the last, it's like 1,265 pixel multiplied by 527. It's like very small places that when you show on the global map that you can actually still see the pattern, but you don't have to load everything. So this is the key of the cloud optimized GeoTIFF. So when you read, for example, I wanted to read some places. I hope you guys can also try to play with that a little bit, but I will show you how to play. Okay, it's not here. Here, browse. Are you guys using QGIS or using ArcGIS or something? Okay.
Yeah, but why do you have minimum value minus 200? It's like a other.
Yeah, you know Black Sea, they have a very they have very low. They're actually minus 300 in the WGS in the EGM 2008. So it's actually happened in Israel. They have a very low place. I was checking some GIS point over there. I was like, what? It's so low. So you can basically go to some places. I recommend go to some places like you're familiar with. For example, this is my island. This is not my island, but the island where I live. So you can pass this link over here. Yeah, there's a Morphe law that every time you try to do something, you might crash because of the yeah, the setup is different from the offers, for example. And you can load this data or direct it into QGIS. And then you can try to use this extract. So raster extract and clip raster by instance. And then basically I would just suggest you to calculate from the canvas. So when you press this button, you can calculate from the canvas. So basically what you see, the canvas, this is the data that you're gonna crop, like crop it to. So when I do some compression, so don't run out too much space on me. And then you can just rush just try to crop them. Maybe the size is still too big. Yeah, I got it. So when I get my local area, I can just remove this layer because somehow when you keep the layer running on your background, when you start moving around, you start creating more data and it might crush your computer. So the wise way is like if you only want to work with this region, you can just remove this. And then you have this digital terrain model of this area, like a small subset. So that is basic things that I will suggest very basic user. I don't think that you guys are basic user, but for the first time they rover this is a good example that you can clip some small space that to visualize. Yeah, it's clear. Yeah, I think Philip have too much experience, so he doesn't even want to move his finger. But yeah, yeah, I work with Philip sometimes. He's a data science, so I have a lot of talk already. Well, all right. Any question? Yeah. Okay. So in here, if you're interested, I also have the article over here on PeerJ. I think you can also search of it. This is kind of like I accidentally add some micro-author. So let's explain about this method, what we use to derive this GEDTM30. And the cool features that I think we did differently is some graphic that we made it here. So we do this kind of global to local modeling. So first we get the global sample of the, what we call it the airborne lidar data, so JEDI and ISAT together. from the global scale, and then we do global model fitting with a few millions of height point with the covariate, and then we do tau-based extra tuning for local terrain, because we actually see through the project the landform diversity have a back impact of the model representation of the local surface. So that is the model that we try to see we can adapt to the local sample and to increase the model accuracy. And some of the result that we shows has, for example, these figures has shows that this method can help really to reduce the height arrow from querying more sample to the local. But yeah, I would not go in detail into this paper, because the main stuff for this workshop is to go something beyond this. So feel free to take a look of this paper, and I will keep moving. Yeah. So we already covered a little bit of this GETM30 and of this project, and then also try to accessing from QGIS. That me wanted to introduce more about the other global digital terrain model and how can all these things together, because when you try to ensemble things, you have to actually understand what data that you are using and how they benefit to your data the ensemble process. So the other data set that we were gonna use is called Merit. So this Merit is the project from, I think, from JEXA from the AW3D30 projects, then the JEXA team and the NASA team, I guess. They tried to create this hydrologic ready digital terrain model. So they have done that. I think this is the first digital terrain model of the whole world. If you say SRTM is not a digital terrain model, yes, this is the first digital terrain model, because some people say SRTM is the first digital terrain model, but it's like a middle of the canopy, between the top of the canopy and the ground. So it's, I would say that it's still like not the digital terrain model, but this one is actually the first one global digital terrain model in 90-meter resolution. So it's rather coarser than our digital terrain model and other state of art, and it's correcting the surface model from currently global open model like SRTM and AW3D30. And this we were trying to use that for our project. And another is delta DTM. So this is the DTM in the 1 arc second. So it's in 30-meter resolution in the equator and maybe a little bit more in the north. And this DTM, they correct the Copernicus DEM with a spaceborne lidar. It's a similar approach, but it seems that they are dealing with the delta, so they use, for example, morphology filter. That's not a machine learning approach to remove the vegetation canopy. Mertz also didn't use, but other paper they use machine learning as we do to remove the canopy, but they didn't use that because they found out like in the coastal area, the surface is supposed to be more flat. It's really flattened than the mountain area. So when you do ISAT point and do interpolations, for example, using the IDK inverse distance, IDW inverse distance weight, yeah, inverse distance weight, you already filter out all of the trees object or building object and try to interpolate with available ISAT point and JEDI point. That's the main target they are using. And they have to do especially well in the coastal area, because the guy who invented this is also working mostly in the Delta area. So this is also what we're gonna use. But most important is that these two data sets are actually are completely open. Otherwise, we cannot merge with them, because we will have some problem to actually make it the open license. because they will try to send you some legal letter and then you have to redo your workflow. So just to be safe that using the when you're using the data, you have to check the license. Yes. So
Just to understand that
yeah.
question in sense, so your model has some issues estimating the terrain, and so now you want to do these more specific models that certain areas will fix that.
Yeah. Yeah, exactly.
Can you just so that I understand, how do you correct for this kind of things in your model? Because I maybe told already about it.
Yeah. Okay. So the way that we correct our model is we try to get some. So we have this spaceborne lidar point as we call the institute data that measuring the ground height.
From institute.
Yeah, from the institute have like a point base. They cover maybe around like 2% of the global land cover because they are mainly high frequencies. So they capture things in the lower resolution, but they did not have the ability to do like a full coverage like an optical sensor. It's more like very sparse lidar sensor, but lidar sensor have the ability to penetrate through the vegetation to the ground. And all this point as the, we call it training sample. And then we try to incorporate the open data, open surface data, like Copernicus data, Atlas data from JAXET. So they are both digital surface model, which capture the top of the canopy in the buildings. And then we add some of the features from accessory data, or we call it like accessory data. So like canopy height model, building height model, to try to learn how can we find the surface, first find the bare earth.
So you actually implicitly canopy height map as well.
Yeah, but honestly, the I would say that the canopy height and the terrain height has optimizing different things.
Yeah.
So it's very difficult to just use the canopy height model and to correct the surface. For example, if you substrate it, some places you have high canopy, but you actually in your digital terrain model, maybe that period of time when they fly through the devices, they didn't have the canopy there, but the temporal differences that we didn't capture will cause to have the peak in the certain places. And some canopy height model will overestimate or underestimate, or like most of them, they will overestimate it in the short height and underestimate with the tall height. And this imbalance also cause some of the problem for the terrain when you do the terrain mapping. So I would say that it's a different optimization problem. But yeah, this is not ideal. I would also say that to map with those problems, because we also learn from just have the canopy height model or like surface reflectance, which is not definitely 100% truth at the time when they fly through all the sensor. So this approach can remove the canopy height, can remove the building, but not perfect. And when we come to not perfect, but not a mountain area, usually the arrow is about 5 to 7 meter. In general, like RMSD 5 to 7 meter. And actually, from my experience, you didn't see so much different, even like 5 to 7 meters. But in the coastal area, 2 meter is very obvious, as coastal area completely too flat, and most of some 2 meter differences already pop up to be very big arrow, for example, to do like fall modeling at the plant area. So that is why most of the we have some coastal product that focus on coastal, because this ecosystem is completely different than the land surface system from the mountain range area. So we try to use different source of the product to see that in this approach, where we can leverage on different sides of the terrain. But the main issue, what we found before, it's that we don't have a complete open 30 meters digital terrain model at the basis to start this process. But now we have this, not perfect for sure, produced by me. They're not perfect, so we try to see that we can improve that. Yes. Okay. So interesting. Yeah. And so this is our some global product. I hope that you can also have time to take a look up for their description and stuff. Also, we try to get some local product just to get started this project. And we test some few sites, and this is the first site that we are trying to do because I've been trying to inquire some product from other places, but haven't heard them back. But this one is already opening the UNDP website. It's about the 10 resolution digital elevation model in Rwanda. And I already checked a little bit of the data. So this is the data, which is the Google satellites in its place. And you can see that if you are a surface model, you will see here is a tall building. It should be pop up with the object over there. So in my point of view, it's quite a good terrain model instead of the surface models. You see that is kind of like we can see this contour line that kind of matching all this. You cannot see from 3D, but you have the sense that, okay, if you see too much, you can see that, okay, this is like a slope, and then there's some object over there, but in this map, you don't see too much object. So, and then we can also go here, and I'll provide some link. Beatrice, will we share some slides in the chat, or where can I share the slides? So we probably can also go through the slides. Yeah. Okay.
Question, so you're local higher, even higher meter.
Yeah.
And still your, this, some of the model is always 30 meters.
This is debatable, but to be consistent and to actually run surface parameter or something, ideally you want more consistent data instead of mismatching. You can see this the clear border line. We call it because it will OpenGeoHub. We did a lot of machine learning model, and that will create, we call it artifact, because you don't it doesn't make sense that the high resolution data even like it's better, but you didn't have the consistency. So you do like a geostatistic and stuff. You will kind of have some issue when you look at them. Yeah. So when you look at the data from here, I'll first share the slides. Okay. Where should I put on the mattermost? So that you can access the slide, maybe get to some link that you don't have to search for yourself. So here, Times Square. Can I put it here? Okay, here. Okay. Yeah. Do you guys have this channel or no? No. Okay, it's difficult. No, no problem, no problem. If you don't have it, it's also fine. Maybe we'll distribute later on the program, so what happened? But we can just show me demo, show my demo.
Do we have this shared Google folder?
We have that. I also put in the shared drive in the same places, so you can just go there. Wow. Okay. I think this is the wrong DP. Why I cannot share? I cannot change anything. Because it's the wrong link. This is the wrong link. It's white. Why I cannot take the link? Okay. Strange. Right, I think I get the wrong link for the places, but I cannot replace it. Why? Oh, it also doesn't work. Yeah. Okay. Oh, it's fine. It's fine. I think I forgot to update this thing. Yeah. All right. Just look at the screen. So this is first of the map I'm trying to query, and there's some also overview of this map. And when you look at this thing, you will find out that the map is actually pretty strange. So here, I don't know what they're trying to do, but they have this kind of like a non-linear or like interpolation of these places that if I use it, I don't know how to find the boundary to actually remove all these places. So this will be some of the problem that we will encounter because most of the source of the data, they don't make it like very easy to easy to use as your use cases. For example, I wanted to do maybe pixel bay aggregation, but you can see these things happen here. It might not be the two ideals for what I'm trying to use. So this is so weird. So you can see these edges. They have this weird structure interpolation, and yeah. So in these use cases, we could try to fix that, or you can try to use a small subset of the data just to improve some of the places, and also at the same time report to them that, we are trying to use your data for this kind of project, but you guys have a problem with this border, and this is what we think that is better for other people to use. And this is most of the case that when we try to do things that we can also report to them because they also provide this open data that you can download from here to use. So what we do, we download it, and then we try to crop into a small subset around the capital. So in this case, you will not actually have a problem right now for the showcase for our showcase, you will not have a problem that to bother by the interpolation. But in the further project, we will try to see that we can contact them and fix this issue. But now we were trying to do is to do a small subset of this data set. But yeah, this is one of the cases that you will meet when you try to use other people's data. And this is the real cases. Okay. And continue. This is one of the sample that we got from Rwanda, a country from Rwanda. They have this UNDP, the digital terrain model map. And another example I wanted to show is to use the map in the Netherlands. So this is one of the Dutch airborne lidar projects. So you can go here to see the view of the airborne lidar project. So you can really see they have some gap, which is water, and also some city, the houses, I guess. So already difference from the terrain model from Rwanda, because this one you don't have any gap in the map. You don't have any gap. They filter out everything, but in the Dutch digital terrain model, you have a lot of gap because they don't want to use the water and want to use the building. So in this case, you already have to think about, okay, if that's happened, how can I do? So that's the first look of the data. And someone can have a guess. Do you know what resolution it should be? What do you think this looks like? Which resolution? Maybe I find some places more diverse that you can try to distinguish. Maybe here. Someone have a guess?
What do you mean? It's
The resolution. So, yeah. Okay, 1 meter. Good guess.
2.5.
2.5 meter.
five.
5? Beatrice?
30 centimeters.
Ah, okay. Good guess. Good guess. So it's 50 centimeters. So so it's a half a meter digital terrain model. So you can see that this is the left side is my global 30-meter map. And the right side is actually the same location, but in their Dutch map. So you can see how rich Dutch people have because they also they try to prevent the flooding, so they need more accurate map to do this kind of analyzings. But you will be jealous that they can have this 50 centimeter digital terrain model of the place. Yes. AHN. Yeah, AHN. It's a national. Yes. And then I think they are keep flying the product, but I got the more complete product, which is AHN4. So you will have a feeling that it's pretty decent.
So
Okay.
by the plate, when it generates the
Um.
images, so where do the images come from that they use for their 50 centimeters?
So they flew the airborne lidar. So airborne lidar is the same sensor that we use for spaceborne lidar, but they have more dense points. So if imagine that how dense in the point in the location can define more higher resolution images. So they basically do interpolation as most of the lidar. They do interpolation even for canopy height. They were trying to interpolation function to get to a raster layer, but it starts from the point cloud. So it's a lot of photon that flying from the sky and then measuring the distance from the ground and to see all this distance between point A and point B. For example, when I reach here and I reach here, they might be 1 centimeter difference, but the spatial differences is maybe 10 centimeter. And if the point cloud can have the higher frequency to actually distinguish these two objects, that can actually map the high differences at this surface, even like in this kind of small set. So in the Dutch way, they just use as much as points to do classification so that they have confidence to derive this 50 50 centimeter terrain model. Yeah. I don't. No.
Well, like in very dense forest.
No. They have reached at all the places. So the lidar will reach the top of the canopy, but also center of the canopy, also the ground. But when they reach the ground, there's no escape that the light will go through the ground and until the core of the earth. So, but if you go through the canopy, yeah, if you're too dense, there's no light, there's no photon falling to the forest. That kind of places, lidar also have difficulty to actually capture the bare surface. But usually if you go to the forest during the day, you can still have light, which is, I don't know, how is the physics terms? The light can go through the surface that actually reach the ground. So that is how they get the ground. But people usually use lidar to derive the forest structure because of this feature, because the lidar fall on different height of the vegetation. So when they return, they can reconstruct the whole tree structure and yeah. Yeah.
The 8 points are higher than 3 meter, 5 meter, then other than that, it's not considered as something like that.
Yeah.
It makes sense.
Yeah. And I think that a classification also a pretty cool research to do, because now I think people still like getting out how do we classify better of the terrain photon and the trees photon, because some signal they are very close. Yeah. Usually you have the lidar signal concentrated on the floor, but also they can reconstruct a tree. But the differences between the bottom of the tree and the ground soil is too close. Maybe 5 centimeter or less, and this is hard for some lidar devices to capture. Yeah. So okay, back to the workshop. Yeah, that is the some introduction of the local DTM we're gonna to use today. And we come to the first ensemble methods. Does anyone recognize this guy? It's an Occam razor. I don't know if you know this philosopher. So basically, the philosophy of this Occam razor is we try to find if we can get as easy as possible to solve the problem, so we don't have to go deeper to a complex things, because this is the truth. So the truth is very obvious if you are, so don't try to find like a difficult way if there's an easier solution. So so this is what we're gonna try for the first one. Okay, there's very easy solution. So we will have the input from Delta DTM, MERT, GETM30, and the national DTM. And then we will do some alignments to actually matching the resolution, because MERS is in the 90-meter resolution. And the Delta DTM has slightly different resolution than the global GDTM, so we try to do also resample. And national DTM usually you have to downscale because they're too high resolution. And when you try to do some matching, maybe it will be mismatch. So we try to align with the pixel size, but as Carly said, maybe can have a way just have a higher resolution at some place and not all of the places. But we try to keep it consistency in this project. And later on, we do some data cleaning, depends on what product we were using. So for example, Delta DTM, we will try to do some rescaling, because they have the scaling factor of hundreds, because they do their measurement unit in centimeter. And then we have to get to meter, so we have to apply the scaling factor. So all these simple things that feed into this computational pipeline. And if you see that this is rather simple, so what we do is actually one step to derive a 10% quantile to see if it works. And later on, we will get GDTM plus. So this is the first method we're gonna use for today. And this is the second method we're also trying to play it around. So this is for the weighted average. So this is also rather simple, but if you can see, there's already a bit more complex than the first one. But these two methods is still rather simple. Let me explain. So the first step that we are using is also get the input and do the alignments and data cleaning. And then the different step is like we overlay with the set point. That way where we use for modeling, but we didn't really capture that well. So we use that as a reference to find the distance to ISAT height from all of the different digital terrain models. So for example, to find from the Delta, to find from the national DTM, to find from MERS, to find GEDTM30. And I would say that every layers could more or less involve with the ISAT point, but not it's still independent in the ISAT, because they go through the modeling process. So you will not actually one-on-one to the ISAT point. So you don't have to worry about when you derive the RMSE from ISAT point, you find the RMSE is 0. That's mainly that they're linear correlated. So you shouldn't use those data. But more or less, when we read the paper, they have been used that for something. For example, Delta, they use that to actually do interpolation, but they add the roughness at the end of the project. So it's still legit. And are using it for modeling. And then we also apply some smoothing. And also we didn't just directly put the ISAT on the value. So we'll see that how it goes when we do the RMSE. So this is what a little bit background of the ISAT. I think I mentioned it a lot of time, but maybe I didn't introduce ISAT. Everyone know ISAT? No? Okay. So ISAT is actually a cool project. So it's a project started with NASA. They used to monitor the floating ice. So they see that the ice moving around the Antarctica or Arctica. and they use this kind of lidar sensor to see that if the ice like floating in some places, so they can capture them. And later on, they found out. So this is the ISAT data that you can see. You have this kind of different photons, and they classify from the ground photon with the canopy photon with the green one, because there are some photon there in the range, and the green point is the top of canopy. And this is like a transect of the satellite. So you can see the satellites here. When you do the transect, and then you give all of the beams to the ground, and the ground represent at this transect, I would say like a line of the measurement, and this will turn into a ground truth point for us to model. And I said they work on this, and then later on they found out this photon can also to be used as land application. So some of the applications using ISAT to map, for example, water places, to example, map the forest and grassland boundary. Some research also using that, and then they start giving out this project. And the initial it's the ISAT product, and then that's, as I say, they have a lot of derived product to monitor different stuff. So for example, there is an inland surface water monitoring using this lidar, and ocean surface water monitoring using this one, and sea ice height is probably the main one. And what we're gonna use for ISAT is the land and vegetation height. So they applied the classification based on the land surface instead of the ocean surface. So this classification of the photons, which derive from the ATL03 product, well, the specific benefit for use for like the land application. So this is the ATL08 product that we are using. And this derived from the blue point, which is ATL03 points. And then actually capture all these photons in the 20-meter segment and try to do the classification in this segment and get the height of the terrain and the height of the canopy from there. So this is I don't know, it maybe not clear for the introduction, but if you have any question, maybe you have to let me know, because maybe I didn't explain in a very structural way. Yeah. Okay.
It's straps. Because it looks like a beat plus 6.
Yeah. Yeah. So it's always 6 straps.
Oh, this one.
Yeah. Yeah. And you see they're like an arm. So they also have a strong beam side and low beam side when the arming somewhere. This is more detail of the satellites, but when you try to see that there is some strong beam and a weak beam, and they will be also have some effect of the data quality. So it's more detail of the satellite size, but for the data user size, you just have to probably find an ARD product, and that would be nice. So that has come to me. So I did create this ARD product, which is I already did data restructuring, because usually the old data they structure with the Orbic according to the Orbic. Wow, it's hard to explain. Yeah. Tomorrow I have another workshop that I can explain this, but it's hard to explain how we visualize this in the Orbic. But this is the data set I produce, where based on geospatial temporal range. So based on the tile of the ISAT that we will use to actually find out all of the point that we wanted to use for example, in Rwanda, for example, in the Netherlands. That is how that we can search that easily, because when you do the orbit base, you have to you don't know what is the next orbit will come over Netherlands. So you have to search for the whole time series to actually find everything. But what we do here, we try to do a spatial temporal restructuring of the original data set, and you make it into a spatial temporal data framework that we can easily query some point from a local side. But there will be more detail at tomorrow's section that probably I didn't have time to cover that over here. Yeah. So this is the data that we're gonna to use from the project that we're saying that we have to use this ISA point from to create this overlay label according to the national DTM, because the national DTM is actually the limitation, because the delta merge DTM and global DTM have covered all of the world, but national then also covers some of the places. So you have to query the ISAT from those places to actually create the accuracy error matrix. Okay. So as we get the second point, we can actually create the accuracy metric, but we also find one issue that it's not easy, which is some places you probably don't have in the same tile, because most of the things that we work for tile, but the country border is not straight into rectangle shape. So some of the time you will have the scenario that one pixel or like one ISA point, they fall into the place where you have all of the data. So GEDTM, merge, delta, and national. For example, you fall on the Dutch coastline, so you will have all of the data. So you can derive the RMSE for 4 of them, the map. But there's also some case that you have the coastline, but you actually the rectangle is falling to like a Belgian border. So you only get the point from the Belgian, but you still wanted to derive the RMSE for this scenario. So this is one without the national, then also could happen in the tile. And the third is only national. For example, the England area of the national, the England area of the nation, that you probably don't have any delta DTM in your country, and then in that case you derive the subset of the only 3 global and merge and national, and the fourth one is only the global coverage, that you don't have any national DTM, you don't have any coastal DTM. Then at that case you derive the RMSE based on global and the global GEDTM30 and the merge. And using the RMSE, we can actually derive the weight. So this is why we need to have the scenario, because when you have 4 RMSE, you actually have to distribute your weight into 4 data. But if you only have 2, you only distribute the weight to the 2. So in this case, if you have scenario 1, you have weight for 4. So you when you do the next step, okay, this is more clearly, it shows that how this scenario impact on the surface, how we compute the ensemble one. Because when we trying to do the weighted average, it's the weight multiplied by the height, and you sum the weights should be 1. That's how you do the weighted average. So in some place, for example, scenario 4, you only have MERT and GEDTM, so I only have these 2 weights. So I only have the weight GEDTM multiplied by GEDTM, and weight MERT multiplied by the MERT. And then you end up to be a height metric of this pixel in this area. And to extend to most of to other area like S2, the scenario is like I only have delta DTM, I don't have national DEM. And I will derive 3 weights from these 3 data, and end up to be the weight sum will be 1, and then I can compute the height of the hostel. Anyway, so this is kind of the concept of this method. So what happened in the tower is like the S4, because they have full coverage. So at least the worst case of the pixel, you have 2 layers. You have MERT and GEDTM, and then you derive, maybe it will be the worst measurement because you only have 2 data. And other pixel, other area like S2 and S3, either you have national DEN or either you have delta DTM. Then you can derive the weight average based on, okay, I have delta DD information, so I have this height of this. You derive the weight from these 3, or you have the national, then we don't have delta, so I derive another scenario based on that. And the best is S1, so you have 4 DEM, so you derive 4 weight, and then you get the weighted average from delta everything. So And the funny thing is that when you derive the RMSE, when you have a higher RMSE, you should have a lower weight. Does that make sense? So when you have the arrow, you have more arrow, you should give it less weight. So we do the inverse of the arrow to see to give it like a weight as an inverse of the RMSE. Yes. Well. So any questions so far? I think it's a.
End of slides. Oh.
Yeah, this is the end of slide, and I wanted to go to some notebooks, so it will be clearly to see that what is actually has been done or this process, right? We have 30 minutes.
Ask. To actually do some kind of use case in Netherlands, and then you tested this one, and then you should be doing it.
Yeah. I'm gonna show these use cases. So I still haven't uploaded this stuff because it's in the in the process of like publication, so I haven't really uploaded. Yeah, but if you're interested in doing this project, I'm also happy like we can write things together. And I didn't upload those, but this is the use cases I'm gonna show. So I have 3 use cases. Maybe I'll show this too. So one is from the Netherlands. So okay, let me just run this. So this Netherlands project. Okay, this is the wrong name. Okay, I'm gonna fix this problem. Yeah. So I created this Jupyter notebook to actually kind of demonstrate that what I just say. There's 2 methods: the method 1, the 10% quanta, the method 2, the weighting average. So the first thing is like I read all this layer, and you can see this link is actually the. So this environment is still in our computing infrastructure back to OpenGeoHub, and I use a VPN to jump back to our infrastructure. So this is just like IP that we internally use with the infinite band. But this is the same as you receive this HTTPS s3.opengeohub.org. It's the same protocol, but we just use like internal protocol to speed up our process. So this is I think we don't have the key, so it's fine to show. So I have the local DTM map in other places because usually I don't put it. We will have a different local DTM, so we just have to point into that local DTM places. So this one is the AHN DTM from the Dutch. And then I'm reading all these files. So we have a global DTM, local DTM, and MERT and delta them. And the first thing that we do is try to get like local boundary of the local DTM. Sorry. So we try to read in the raster IO, and then you can see that here when you see the projection is different. So we try to first also reproject everything. So this is the projection in the 28992, but most of the global DEM, they are in the projection of the EPHG 43226. So we have to do some reprojection. So this is just an automated function to find the bounding box in the EPHG 4326. And later on, we can run this g.warp function to align all of the tile into the same place. So when we get the bounding box, which is the bounding box are our Dutch DTM, and then we create some folder and we start processing our data. So slowly you can see that all of the data, because the global data have the global range. So I need to crop to the national DEM range. So in order to aggregate them, so this is the process that we do, slowly cropping like all of the data set into Dutch Dutch range. But also in this process, we also crop the Dutch one because this one is in the 50 centimeter, right? So we try to make it aggregated to a 30-meter resolution in order to do pixel alignments for the process. So we also process them in this range. Okay, so I get all these 4 layers right now in my local environment, and then I can read them in. So this is just some setup from the template, and this is the function I developed by my colleagues. So just like easier ways to actually aggregate them to a data frame. So when you see here, I just have to read them into the memory. So as you see that if you have the local file, TIFF file, so you have to read in the memory as an array. And now I'm using Python, so it's a NumPy array that I'm reading. So you can see that this is 4 layer from 4 different layer, and this is pixel we flatten into 1 dimension to actually speed up. And if you're interested with this function, that we have a library called scikit-map. So this is more mainly internal use by OpenGeoHub. That we, because we did a lot of high performance computing in a global scale, so we developed this library to actually read a TIFF file in the vast array allocation. So it's not for every use cases, but for internal use, we do different with this allocation and read the file from this directly.
Is it cloud-based computing?
It's not the cloud-based computing. No, it's we use the protocol for S3 protocol to read the file, but the computing it's always in-house as cloud. If you say that, yeah. So we use the protocol as the S3, but to actually reach the fast computing in the house, you have to build the InfiniBand across the server. So that you cannot stream the data from the Ethernet cable. It will be too slow. So that's why I think the bottleneck is not the software, but
Yeah.
so wow, it's a lot of stuff. But here is how we read the data, and then now we read this data, and then we can actually plot the data to actually see. Wow! There's some message popping up. So this is the data that we first load and plot in the Python environment. So you can see that GEDTM30. I actually didn't download all of the files for the Dutch one because it's just a bit too much. And this is how you showed off the map, and you can see that there's the same legends, and Delta DTM have very weird pattern than other 3. So other 3, at least you can see that the pattern is quite the same. But this is the only reason of the Delta DTM, they have like a 100-meter scale. And also, these plates are all blue because they play the pixel that above 30 meters into 999 as their default non-data. So you can see that this is not realistic. So we have to actually clean it up. So we define where is the no data of the Delta DTM, which is the 3rd index, and then we send it into the non-data.
Scale wrongly because of that extreme. Oh, that's why it's because of those high values. It's puts everything at the same scale, then it looks different because
yeah, exactly. So here's the place that we do the rescaling of the delta, and also we assign the local DTM node data to actually clean up, and then you can see after all. You can plot it again. Yeah, after we rescale the data and then clean up, we can see that this is actually how it looks like as a scale of the value local DEM and the delta DTM compared with MERT. And so basically, this changed the most. And then we can create the mask. This is the mask for the function 2. So basically, you calculate the non-value of four different dam and find the condition of S1 is like there's no non-data. The pixel have no non-data across four layers, and that will be count as the valid mask. And then we can create four masks. So the mask one is we have data for four of the dam. So this is about 220 million pixels. And S2 mask is the data we have with the national dam, and it's about the similar pixels number. And the max 4 is like we have the data for GEDTM30 and the merge, so it's have more pixel for sure. And the first one, we try to derive the quantile of DTM, and then we do this one single line function, non-percentile, to actually create the 10 percentile of the data. And this function we rewrite over here is simply because the NumPy function is pretty slow. So when you do large computing, you are considered you will meet the problem that if you derive the non-percentile with the default NumPy function, that will be pretty slow. And this function we rewrite over here is from the stack overflow issue that because people complain that it's too slow. So they try to rewrite a function and they just copy paste from there. So basically they rewrite the basic algorithm to actually doesn't keep the original data in order to speed up the data rewriting on the data format. So it's become pretty fast using this function. And then we can save this map because I already derived this method one. It's quite simple. And then we can save it and show it already. So it already saved it here, the result of the method one, 10% quantile. It's only, so the method is just this line. Okay, 10% quantile, and then we have the method. But most of the code that we try to clean the data has this much of coding. So you can see that this is mainly a data science job is to clean the data, then derive the methodology. And the second one is to use the not the user accuracy, iSet accuracy. Yeah. So that's one we are trying to incorporate with the iSet. So we first read the raster, we come to the boundary of the our national dam. So because we want to query the iSet for this tile, so we first get the boundary of the dam, and then we start query the iSet from the website I just provide over here. So here's the place that I can just get the GeoJSON, which record all of the entries of the iSet tile over here. So I have all of the iSet data in one table, and then I can do the intersection to actually get the iSet which fall into my Netherlands range. And then we do this, and then we can find out there's only 12 iSet tile that fall into this. So we only have to query all these 12. And then we use this function. We use DuckDB to actually do a SQL query. Tomorrow I will also talk a bit more about this, but this is just a way that we can do a lazy loading query for most of the URL at the same time. So 12 URL we can just query in one function and get everything, and using this latitude and longitude as the predicate to retrieve all the data. So we spend like 3 seconds to get all the data, which is I think, yeah, about 2 million? Yeah, 2 million points data that we can query for the Netherlands. Yeah. No, the different year is just you can also query. For example, you're only interested in the year of IXA in 2019. You can query 2019. In case I don't care, because terrain it doesn't change that much as canopy. So maybe more of a canopy issue. Probably wanted to query different year to map yearly, but this one I don't carry. And then we do the space overlay, also the function developed by us. And we can overlay the eyesight point already directed with all of the DTM tile. So this place is to read all of the layers from the local site and try to do the space overlay here. And this function, we also rewrote space net overlay function by ourselves in order to query the data from the disk. So it's just the most efficient way. For example, here is 2 million of the point, and then we can do parallel overlaid based on the function defined. So it's rather fast to query this 12 million point and overlay with 4 layers. I think in a matter of seconds, like 20 seconds, you can finish all the overlay. So this is for here. Yeah, now they are try to query different block for each point. So basically the function design is I have the point and I will point to the geolocation with where the data in the disk where they're located, and then try to only retrieve the block because the GeoTIFF is actually organized block by block. You have a block size of the tile. Maybe the block is 256 or 1024, and then you only retrieve this small block. You don't retrieve the whole GeoTIFF from the disk. And in this way, you can do a fast query. So here I already finished the overlay. So in the matter of second, I can do 2 million overlays from here. Okay. And later on, we do some high correction. Do you know why we need to do the high correction? Yeah, because the eyesight data is in WGS 84 projection, and most of the global digital terrain model is in the gravity model EGM 2008. So they have a gravity issue with high when you observe from episoil or the gravity model. So you have to convert it into the height. So this is very simple. Otherwise, some place you have 50 meters offset that you don't know why, just because you didn't run the correction. And this correction is, you can find it online. It's called GeoID, GeoID. And later on, we also have to scale the delta. How many minutes I have? Huh? 10? And then we can derive the weight function. And then we can compute the weight very fast. This is very fast, so that's why I say that it's simple. So the scenario one, you have only 2 layers. So you only compare the RMSE from 2 layers. This is scenario 1. Yeah. 2, 3, 4. Scenario 1, you have 4. Sorry. Scenario 1, you have 4 layers. Every layer is available, so you compute the RMSE for 4 layers. And so you can do the inverse and actually get the weights. So if you see here, this is the weights I put in GEDTM30 because the RMSE is 1, and it's higher than the local DEM. Lower than is 0.8, then the delta DEM 0.6. So they have higher accuracy, so they receive higher weight for lower RMSE. So it's more representative they are showing here. So the scenario 2, 3, 4. And then I calculated the weight into 4 different scenarios. Well, and this figure shows better of how this 4 scenario looks like. So this is the 4 different scenarios. Scenario 1 is where we have 4 data, which is, I supposedly it's this area that have 4 layers, because this is completely screwed. Because this is not meaningful, because the scenario 1 for this pixel doesn't mean anything. They only have the benefits of all this pixel, which had the 4 different layers of DTM. And the scenario 2 and 3 and 4 is like only global and GDTM and merge, so they have all of the pixels, so it's more complete. So what we're trying to do is we get the pixel 4 we had the EDTM as scenario 4 and replaced by 3 and 2 and 1. So improve those pixels that they have better prediction. For example, this area. And this is what we're trying to figure out what is the mask, like what is the pixel has been valid for each scenario. So scenario 4 is everything, and 1 is smaller than 2 and smaller than 3. And in this way, we can just simply do like a pixel replacement for EDTM for S4. So S4 has the base map, and I replace a pixel by the max we have, the mask we have over here, to replace only pixel in that in that pixel in that place in of the matrix, I would say. Yeah, and then I can compute the yen. Well, I don't have too much time. Maybe I jump to the last one. So I also did the one from the Kigali. You know where is Kigali? It's the capital of the Rwanda. So I take a Rwanda map, but I only crop the capital province so that I can have the free of the arrow that we see over here. So this is the arrow that we have. So we just have to get the arrow free over here. And this is the GEDTM and local. And because it's an inland country, so you don't have any delta 10. So in this scenario, you have only 3 ensemble. And I can run everything and got here. And that will be pretty fast because Kigali is way smaller than the Netherlands. Okay. So it's the same process that we can run for the Netherlands, but also run for different places. Yeah. Where I stop? Yeah, I try to read the table. This function always pretty slow because it's got my covariate from the Google Sheet. When everything comes to there, it's becomes slow. And now I also start to overlay with the exact point, but I already have the master one data. So, and can I download it? Yeah. Okay. So this is the map that scenario 1 and 2, because they're involving the delta DTM, so they don't have any valid pixel. And scenario 2, using the national DEM, so you can see that in this national range, in this Kigali range, you have a valid pixel, and they will be aggregated with scenario 4. And this is the mask. And we also compute a little bit of the hell shade to see like how it looks like, because when you see the height, you usually don't find that really meaningful at the edge of the DTM, because it's hard to visualize, but you can visualize by the hell shape. And also like this is the specific catchment area. And I want to show the last things. So as I download the method 1 and method 2, and I can also download yeah. So here, so also the local DEM. So I want to see one very important thing at the end. So, yay. So we can derive the hell shape for the different method. Okay. Okay. So let's compare. So the last thing we're trying to do is, because we are merging using the range of using different dam, and some dam they didn't have the correct range. It doesn't cover like all the pixel in the tile. So if you see that at the tile boundary, you can actually see some artifact. If you see some artifact, it actually means that the consistent is not, it's not correct. So for example, here, close it down. This is local Kigali Hell-shaped map. And if I do weighted average, you can see here, this is more or less the area of Kigali. And the more important thing to see is actually see from the average, see from the result, see if they have any issue at the boundary. Because, for example, in this hell shade, if you have the boundary at local, it means that there is so much differences between using a local dam and the only global dam. If it's have a big difference, it means that the method is actually bad because it doesn't really represent like consistent terrain of the edge. So this is always important to derive all this map, not only to see the terrain map, but also like this kind of hell-shaped map to see that, okay, you know, also can compare a little bit of the good or bad of our different, two different methods. So it's always a good way. So for example, here, here's the weighted average. And this one is P10. I don't know which one do you think is better. So you proved that the all-six razor doesn't work. We still have to work on more complex model. Anyway, this is I think we have to wrap up the presentation. But yeah, it's maybe I get so exciting to talking something much like that really, and the rest of the presentation with more interactive code. But thanks everyone for joining this workshop. Yeah,